we have learned about the joint probability density function with multiple random variables, right? So this is the example 5-20 about the component lifetimes. In an electronic assembly, let the random variables x1, x2, x3, x4 denote the lifetimes of 4 components in hours. And suppose that the joint probability density function is given the following equation, okay? fx1, x2, x3, x4 is equal to 9 by 10 to minus 12th power by exponential minus 0.001 x1 minus 0.002 x2 minus 0.0015 x3 minus 0.003 x4. And in this case, all the random variables x1, x2, x3, x4 are larger than 0. Okay? And in this case, what is the probability that the device operates more than 1,000 hours without any failures? That is the question. For this question, we have to calculate the probability of x1. x1 should be larger than 1,000. And x2 should be larger than 1,000. And x3 also should be larger than 1,000. And x4 should be larger than 1,000. Okay? Because we have to find out the probability that the device operates more than 1,000 hours without any failures. So all these 4 random variables should be larger than 1,000. And based on the previous slide, what about this? That is equal to the integration, first integration, right? From 1,000 to infinite. The joint probability density function fx1, x2, x3, x4, x1, x2, x3, x4, dx1, dx2, dx3, and dx4, right? Okay? Please check your previous slide. So this probability is equal to the first integration of the joint probability density function from x1 to x4, okay? And all the random variables should be larger than 1,000. So from 1,000 to infinite, okay? And this is equal to the first integration, okay? 9 by 10 to minus 12th power, okay? By exponential minus 0.001 x1 and minus 0.002 x2 minus 0.0015 x3 minus 0.003 x4 dx1, dx2, dx3, and dx4. Right? Okay? So in this case, we are going to first calculate the dx1. Okay? So we are going to first calculate this term. And we can say this is the small a. And small a is equal to the 9 by 10 to minus 12 power by exponential. These terms can be extracted, right, from the integration, okay? Because we are going to integrate about the dx1, right? So that is equal to 9 by 10 to minus 12th power by exponential minus 0.002 x2 minus 0.0015 x3 minus 0.003 x4 by integration from 1000 to infinite exponential minus 0.001 x1 dx1. Okay? Right? And what about this? That is equal to minus exponential minus 0.001 x1 over 0.001 from 1000 to infinite, right? And in this case, we can eliminate the 0.001 by dividing 10 to minus 12th power. So 10 to minus 9th power will be left, right? And what is the exponential minus infinite? That is equal to 0, right? So this is equal to minus 0 plus exponential minus 1, right? And as we can see, this equation, if we repeat this calculation to x for the x2, x3, and x4, we can simply obtain the following answer. That is 9 minus 10 to minus 9th power by 1 over 0.002. Okay? This is from this term by 1 over 0.0015. Okay? This is from the x3 by 1 over 0.003 from the x4, right? And by, there is a exponential minus 1 here, okay, from the x1. And what about the x2? This will be exponential minus 2, right? Right? If you repeat the same calculation to the x2, the range is from 1000 to infinite, right? So exponential minus infinite goes to 0. So if you multiply the exponential minus 0.002 by 1000, it's exponential minus 2. Okay? And also, there is exponential minus 1.5 from the x3, and also exponential minus 3 from x4. Right? And in here, what is this? 9 by 10 to minus 9th power, right? Right? So this can be eliminated. So the final answer is equal to this exponential minus 1, minus 2, minus 1.5, minus 3, okay? That is equal to exponential minus 7.5, okay? And that is equal to 0.00055. Okay? So if you calculate this based on your scientific calculator, the answer is 0.00055. So that is the answer for the example 5-20, okay? And now, we are going to discuss about the marginal probability density function for the case of the multiple random variables. If the joint probability density function of continuous random variables from x1 to xp, the equation is expressed by the following equation. That is x, f, x1, x2, blah, 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 xp. That is the joint probability density function, right? For these multiple random variables. In that case, the marginal probability density function of xi is given the following equation, okay? The marginal probability density function of fi fxi is equal to the integration of the joint probability density function over the reason Rxi. Okay? This is the same formulation with the previous, the marginal probability density function with a single random variable, right? So this is the exactly identical formulation, but only difference is that the number of random variable is increased, okay, from one to multiple. And also, in the case of the multiple random variable case, we are using the joint probability density function rather than the normal probability density function, okay? And this integral need to be over all points in the range of x1, x2, xp when xi is equal to small xi. So that is the definition of the marginal density function for the case of multiple random variables. And this is about the mean and variance, okay? The mean and variance of xi is determined from the joint probability distribution as follows, okay? And this is the mean. The mean is equal to the integration xi by the joint probability density function, right? From x1 to xp, okay? And in the case of the previous single random variable, the mean Ex was integration from minus infinite to infinite x by the probability density function, right? Do you remember that? This is the exactly same formulation, but the only difference is that the number of random variables is not one anymore, okay? The multiple random variables are applied. And what about the variance? For the case of the single random variable, the variance was the integration of x minus mean mu square by the probability density function, right? So in this case, the identical formulation also can be applied, but only difference is that this normal probability is changed to the joint probability density function, and also the number of random variables are increased to multiple case. Okay, but the equations are exactly the same. And this is about the conditional probability distribution and the independence. The conditional probability distribution and independence are identical to those introduced in the previous chapter for the discrete random variables. For example, the conditional probability density function of x1, x given x4, x5 can be expressed by the following equation, okay? This is the conditional probability function, right? And the conditional probability function is equal to the ratio of the joint probability density function and the marginal probability density function of x4 and x5, okay? So the identical formulation is also applied to the case of the continuous random variable. But in this case, the marginal probability density function of x4, x5 should be larger than 0. Why? Because this is used for the denominator. Okay? And what about the independence? Independence, in the previous chapter about the discrete random variable case, the joint probability density function, okay, is equal to the multiplication of the marginal probability density function of each random variable when the random variables are independent, okay? And this can be applied for all random variables from x1 to xp, okay? So this is the example 5-23. And suppose that x1, x2, and x3 represent the thickness of a substrate and an active layer and a coating layer of a chemical product. And assume that X1, X2, and X3 are independent, okay? This is very important. They are independent and they are normally distributed, which means that normal distribution can be applied, okay? With these three means and these three standard deviations, okay? So in this case, the specifications for the thickness of the substrate active layer and the coating layer are between 9,200 and 10,800 for the case of the X1, which is the substrate, and between 950 and 10 and 1,050 for the case of X2, that is the active layer, and between 75 and 85 for the case of X3, that is a coating layer respectively. And in this case, what proportion of chemical product meets all thickness specifications? That is the question. So we need to calculate the probability of X1. X1 should be between 9,200 and 10,800, and X2 should be between 950 and 1,050, and X3 should be between 75 and 85. So we need to calculate this probability, right? And from the example, all the random variables are independent, which means that this can be changed to the multiplication of each probability. Right? Right? Because this is the independence. And also, the random variables x1, x2, x3 are normally distributed, which means that we can apply the normal distribution, right? And also, we can use the standard normal random variable, right? We can say that is Z normally. So that can be written as the probability of Z1, right? This is the standard normal random variable, and they should be between 9,200 minus, what is the mean? That is equal to 1,000 here, okay? 10,000, sorry, 10,000. 10,000 over, what is the standard deviation of x1 case? That is 250. There is a 250 here, and this can be 10,800 minus also 10,000 over 250, okay? And by the probability of Z2, right? This is the standard normal random variable for the case of x2, okay? So that is equal to 950 minus 1,000, okay? And over 20 here, okay? And this is also 1,050 minus 1,000 over 20, okay? and by the probability of Z3. Z3 should be between 75 minus 80 over 4, and that is 85 minus 80 over 4. Okay? And this is equal to the probability of Z1 between minus 3.2 and 3.2. Okay? And by the probability of Z2, that should be between minus 2.5 to 0.5, right? By the probability of Z3, Z3 is between minus 1.25 and 1.25. Okay? And if we want to use the appendix table, this should be changed to the probability of Z1 should be smaller than 3.2, right? Minus the probability of Z1 should be smaller than minus 3.2, right? Right, do you remember that? Okay. So this is exactly identical to this equation. And also, this is the probability of Z2 smaller than 2.5 minus the probability of Z2 smaller than minus 2.5 by the probability of Z3 smaller than 1.25 minus the probability of Z3 smaller than minus 1.25. Okay? So now we can simply use the appendix table, okay? And if you calculate this equation based on the appendix table, the answer is 0.99862 by 0.98758 by 0.7880, okay? So that is equal to 0.7778. So the equation can be simply solved based on the appendix table. Okay, that is the answer. Okay. And now we are going to discuss about the covariance. Okay, covariance is called 공분산 in Korean. And the common measure of the relationship between two random variables, x, y, is called the covariance. Okay? So the reason why we use the covariance is to determine the relationship between two random variables. Okay? Okay? We are going to find out the relationship between two random variables, that is the covariance. So if the covariance is equal to the 0, which means that there is no any proportional relationship between two random variables, x and y, which means that they are scattered without any relationship. Okay? And if the covariance is larger than 0, which means that it gives the positive value, the random variable y increases when the random variable increases. Okay? So when both random variables are increased, we can say the covariance has the plus value, okay? And when the covariance is the minus value, the random variable y decreases when the random variable x increases, okay? They give the opposite relationship, okay? And this can be minutely explained in the later slide again about the correlation. And to define the covariance, we need to describe the expected value of a function of two random variables, h, x, y. And in the case of the covariance, h x comma y is equal to x minus the mean of x by y minus mean of y. Okay? That is the equation to solve the covariance between the two random variables. The random variable x minus the mean, okay, by the y minus the mean of y. Okay? Based on this equation, we can determine the relationship between these two random variables. Okay? So the average value of the h x comma y is given the following equation. That is, the average h x comma y is equal to the double summation h x comma y by the probability mass function. Okay? This is the case of the discrete random variable. And in the case of the continuous random variable, that is equal to the double integration. Okay? hx comma y by the probability, the joint probability density function fxy. Okay? This is the case of the continuous random variable. So based on this hx comma y formulation and this relationship, we can determine the covariance, the relationship between the two random variables. Okay? And this is the example. For the joint probability distribution of two random variables in the following figure 5-12, as you can see here, based on this figure, please calculate the average x minus mu x by y minus mu y. Okay, that is the equation, and that is the question. And to solve this equation, we first calculate the mu x and mu y, right? And in this case, in the case of the previous conditional mean, we have already learned about the conditional mean, right? The conditional mean mu y given x y was equal to, this is the discrete case, right? Okay, this is not the continuous case, this is the discrete case. And that was equal to the summation y by the conditional probability mass function. Okay? We have already learned about this equation in the previous class. And this is about the conditional mean for the case of discrete random variable, right? And we can use the identical formulation. This case, we have two random variables. And in this case, we have to only calculate the mean of x, which means that this is the marginal mean. Okay? So the marginal mean, mu x, okay, is equal to the summation of x by the joint probability, the marginal probability density function. The marginal probability mass function, because this is the discrete case. Okay? This is exactly the same formulation. Okay? The conditional mean is changed to the marginal mean. Okay? And the conditional probability mass function is changed to the marginal probability mass function. Okay? So we need to use this equation. Okay? So we are going to first calculate the mu x here. That is equal to large E, large X. Okay? And this is equal to the summation from X is from 1 to 3, right? 1 to 3 X by the marginal probability mass function of Fx, right? That is the equation. Okay? And in here, what is this? The marginal probability mass function is also equal to the summation of y, the joint probability mass function. Right? Okay? Please see your previous slide. Okay? So for the case of the discrete random variable, the marginal probability mass function of x is equal to the summation of y and the joint probability mass function fxy. Okay? We have already learned this equation. So this can be changed to the double summation, right? And the first one is from, x is from to 3. And what about the y? Y is also from 1 to 3. Right? And x, y, the joint probability mass function, fx, x comma y. Okay? And in here, the joint probability mass function is already given based on this figure, right? This is the joint distribution of x and y. So this can be calculated by when x is equal to 1, x is equal to 1. By, what about the joint probability mass function when x is equal to 1? We have two options, right? 0.1 is when y is equal to 1, and 0.2 is when y is equal to 2. So this is the joint probability mass function of x and y from y is from 1 to 3, which means that this should be 0.1 plus 0.2, right? When x is equal to 1, we have two different, the joint probability mass function here according to the y. And this is the double summation, which means that we have to also consider about the y from 1 to 3, which means that when x is equal to 1, we have to consider these two values. Okay? X is equal to 1 and y is equal to 1. Also, x is equal to 1 and y is equal to 2. Okay? So this is the summation here. Plus, when x is equal to 2, there is no joint probability mass function here, right? So 2 by 0, okay? And when x is equal to 3, we have three options here, okay? 0.2, 0.2, and 0.3. So that is equal to 0.2, 0.2, 0.3, okay? So this is equal to 0.3 plus, and what about this? This is the 0.7, so this is 2.1. So the answer is 2.4. Okay? So we already calculate this value here. That is the 2.4. And also, we need to calculate the mu y. This is the marginal mean of y, right? And this is the same formulation, okay? So this is the double summation, okay? From x is equal to 1 to 3, y is equal to 1 to 3, y by the joint probability mass function fxy. Okay? So this is the identical formulation, and when y is equal to 1, y is equal to 1, we have two options here, okay? That is, the first one is the 0.1, when x is equal to 1, and the second one is the 0.2, when x is equal to 3. Okay? So this can be when y is equal to 1, we have two probability, that is 0.1 plus 0.2. okay, here. And when y is equal to 2, we have two options here also. That is 0.2 and 0.2, okay? So 0.2 plus 0.2 plus, when y is equal to 3, we only have one probability mass function that is equal to 0.3. So this can be 0.3 plus, what about this? 0.8, okay? And that is 0.9. So the answer is 2.0. So this is equal to 2.0. Okay? And finally, we need to calculate the average x minus mu x by y minus mu y. Okay? And this is equal to the double summation, okay, from y is from 1 to 3 and x is from 1 to 3, okay? And this is x minus mu x by y minus mu y by the joint probability mass function fx x comma y. Right? Please see your previous slide. This is the hx comma y. Okay? So this is this formulation. Okay? Double summation hx comma y is equal to this equation, and by this is the joint probability mass function. Okay? So this should be equal to, when x is equal to 1, okay? 1 minus, this is equal to 2.4, okay? And when y is equal to 1, that is 1 minus 2. By, when x is equal to 1 and y is equal to 1, the joint probability mass function is equal to 0.1. So 0.1 here, right? And plus, when x is equal to 2, when x is equal to 1, okay? And when y is equal to 2, okay? When x is equal to 1 here and y is equal to 2, that is 0.2. Right? Plus, when x is equal to 1, by when y is equal to 3, the joint probability mass function is equal to 0, right? There's nothing here. Okay? Plus, when x is equal to 2, okay? This is for all cases when x is equal to 1. Okay? This is the y is equal to 1, and this is the y is equal to 2. This is the y is equal to 3. Okay? So we considered all these 3 points here. And what about this column? All the equations should be equal to 0, right? So we are not going to consider when x is equal to 2. Okay? And we need to consider about this case when x is equal to 3, okay? So when x is equal to 3, 3 minus 2.4 by, when y is equal to 1, 1 minus 2 by 0.2 plus 3 minus 2.4 by 2 minus 2 by 0.2 plus and 3 minus 2.4 by 3 minus 2 by 0.3. Okay? So, if you calculate all this equation, the answer will be 0.2. Okay? Okay. So, the covariance for this case is equal to 0.2, which means that when the random variable y increases, when the random variable x increases. Okay? Okay? Because this is the plus value. And this can be explained in the later slide when we discuss about the correlation. So this is the definition of the covariance. The covariance between the random variables x and y denoted as C of v x comma y or sigma xy is given the following equation. Okay, this is the covariance of xy. Sigma xy is equal to the E x minus mu x by y minus mu y. And this is also equal to the mean of xy minus the multiplication of marginal mean of x and marginal mean of y. So I'm going to derive how we can obtain this equation from this relationship. Okay? So the mean x minus mu x by y minus mu y is equal to the double integration for the case of the continuous random variable, okay, from minus infinite to infinite, okay, that is equal to x minus mu x by y minus mu y and fxy dx and dy. Okay? This is the definition, right? And in here, this can be written as the double integration x by y, okay, minus x mu y minus y mu x plus mu x mu y by the joint probability mass density function here. Right? Right? This is this. Y by x by y and minus x by mu y and minus y by mu x and plus mu x by mu y. Okay? So we can express this equation as you can see here. And in here, we are going to first consider this term. Okay? So we can say this term, we consider this term is equal to small a. Okay? So small a is equal to the double integration minus infinite to infinite y mu x fxy x comma y dx and dy. Okay? So in here, we can have 4 different equations. That is xy by fxy. Okay? That is the first one. And also minus x by mu y and fxy. Okay? And also we have this one and this one. Okay? So in this case, we are going to first calculate this term. Okay? So we can say this is the A, and A is expressed by the following equation. Double integration y by mu x by the joint probability mass function dx dy. Okay? Do you understand? So in here, the mu x is the constant value, right? So we can extract the mu x from this integration. So mu x by the double integration from infinite to infinite, minus infinite to infinite, y by the joint probability density function. Right? And in here, what about this? We only consider this one, okay? That is the integration from minus infinite to infinite. The joint probability density function, fxy, dx. What is this? That is the marginal probability density function of y, right? That is equal to the fy. Okay? Please see your previous slide. That is around 40 or 42 pages, okay, in your class notes. So that is equal to the marginal probability density function of y. So this can be written as the integration from minus infinite to infinite y by the marginal probability density function of y dy. And what is this? That is equal to mu y. Okay? Okay? So this is equal to mu y. Okay? So the A is equal to mu x by mu y. Okay? And what about this case? So this is equal to mu x, mu y, and this is also mu y, mu x. Okay? If you repeat the same procedure, you can obtain these two values. So which means that this can be written as the double integration from minus infinite to infinite x, y, fx, y, okay, dx, dy, minus mu x, mu y, minus mu x, mu y, plus mu x, mu y, double integration from minus infinite to infinite fx, y, x comma y dx dy. Right? Okay? in here, what about this? The double integration from minus infinite to infinite of the joint probability density function. That is equal to 1, right? So we can eliminate these two, okay? And what about this? That is equal to mu xy, okay? The mean of xy. So this can be rewritten as mu xy, this is equal to large E, large X, large Y, minus mu x and mu y. Okay? So, for the case of the covariance of x and y, we can simply calculate this based on this relationship. The mean of xy minus the multiplication of the marginal mean of each variable. Okay? So this is the definition of the covariance. And now we are going to learn about the correlation. And this is the definition of the correlation. The correlation between random variables x and y denoted as rho xy. Okay? And rho xy is equal to the covariance of xy over roots the marginal variance x by the marginal variance of y. That is the definition. And for the case of the correlation, we have the special cases. Cases, and because the roots, the marginal variance x should be larger than 0, right? Because this is the root term. And also the roots, the variance vy should be also larger than 0, okay? And if the covariance between x and y is positive, negative, or 0, the correlation between x and y is also positive, negative, or 0 respectively. So the rho xy should be between +1 and -1. And this means that this is the random variable x, and this is the random variable y. And we can draw the linear relationship, okay? We can say this is the y is equal to ax plus b. Okay? And if we obtain the two random variables, and the two random variables are exactly on this plane, this line, okay? In this case, the rho xy is equal to +1. Okay? Because the two random variables have the linear relationship, okay, in the positive direction. So in that case, the rho xy is equal to +1. And when there is a x and y, and we have this kind of negative relationship, that is y is equal to -ax plus b. And if the two random variables are placed on exactly on this straight line, okay, in this case, the rho xy is equal to -1. Okay? Okay? So if you calculate this value, if you obtain the +1, that means these two random variables have the linear relationship in the positive direction. Okay? And if you calculate this equation, and if you obtain the -1 value, these two random variables have the linear relationship, but the direction is minus. Okay? And what about this case? if the data points are placed on near the straight line. In this case, the low xy is between +1 and 0. Okay? This means that the two random variables have a proportional relationship, okay? But that has not the exactly linear relationship, okay? But they have a kind of relationship. And when y increases, when the random variable y increases, and the random variable x also increases. So in that case, we obtain the positive low xy, but the value is between +1 and 0. Okay? Because the data points are not exactly placed on this straight line. Okay? And what about this case? There is the x and there is the y, and we have this linear line, that is y is equal to minus ax plus b, and we obtain this kind of data point here. The low xy is between 0 and -1. Okay? They have a relationship, kind of relationship, but they have a negative direction in this case. So in this case, the low xy is between -1 and 0. Okay? If the data points are exactly placed on this straight line, linear relationship, the low xy is equal to -1. Okay? Okay? And what about this case? This is the x and this is the y. We have this kind of relationship. Okay? In this case, the low xy is close to 0, which means that there is no any proportional relationship between x and y for this case. Okay? So, based on this definition of the correlation, we can determine the relationship between the two random variables, x and y, okay? Whether they have a positive relationship or the negative relationship and the scantiness of the data point, okay? So, this is very good method for the engineering field, okay? And this is the example 5-26 about the covariance and the correlation. For the discrete random variables x and y with the joint distribution shown in this figure 5-14, determine the covariance sigma xy and the correlation rho xy. That is the question. So first, we are going to calculate the sigma xy. That is equal to the mu xy minus mu x and mu y. Okay? And this is the discrete case, right? This is not the continuous case. This is the discrete case. So the mu xy is equal to the double sigma, right? From x is equal to 0 to 3, and y is from 0 to 3, right? And in here, and then this is the joint probability mass function fxy. Sorry. This should be x by y by the joint probability mass function. Right? So we need to calculate this equation. And here, when the x is equal to 0 and y is equal to 0, even though there is a probability here, this is equal to 0, right? We have to multiply 0 and this probability, okay? So we are not going to consider the value with the 0 in here, okay? That means we need to only consider these 5 data points, right? Only these 5 data points. So when x is equal to 1, that is, when x is equal to 1, and when y is equal to 1, and the probability is 0.1 here, okay? Plus, when x is equal to 1 and y is equal to 2, the probability is equal to 0.1 here, okay? And plus, when x is equal to 2, y is equal to 1, the probability is equal to 0.1. And when x is equal to 2, y is equal to 2, the probability is equal to 0.1. And when x is equal to 3 and y is equal to 3, the probability is equal to 0.4 here. Okay? Right? So, if you calculate this value, the answer is 4.5. Okay? So, this is equal to 4.5. And then we are going to calculate the marginal mean of x. That is equal to the sigma x is from 0 to 3 x by the marginal probability density mass function fx, right? Right? And this can be rewritten as the double summation y is from 0 to 3, x is from 0 to 3, x by the joint probability mass function. Right? Right? Because this is equal to the summation of joint probability mass function. Okay? So, when x is equal to 1, the joint probability mass function should be the summation of these two values. Okay? 0.1 plus 0.2. And when x is equal to 2, we have also two values here. That is 0.1 plus 0.1 plus when x is equal to 3, that is 0.4. Right? Here, sorry, yeah. This is the 0.1, right? So that is equal to 0.2 plus 0.4 plus 1.2. That is equal to 1.8. Okay? So this one is equal to 1.8. And the mu y is equal to also the double integration. X is from 0 to 3, y is from 0 to 3, y by fxy, x comma y, okay? That is equal to, when y is equal to 1, we have two probabilities. That is 0.1 and 0.1 here, right? Okay? Right? So that is equal to 0.1 plus 0.1 plus when y is equal to 2, we also have the 2 probability, that is 0.1 and 0.1, dependent on the value of x. So that is also equal to 0.1 plus 0.1 plus when y is equal to 3, only one probability is here, that is 0.4. So this is equal to 1.8. Okay? So this is also equal to 1.8. So the covariance is equal to 4.5 minus 1.8 square. Okay? That is equal to 1.26. Okay? 1.26. Okay? So this is end of today's class. And see you on Friday.